Hi there, I'm author Leshkowitz, and I'm going to be talking about repetition languages. This is a joint work with Kupferman. First, some basic definitions. Buki automata are automata over infinite words. The language of a Buki automaton is all infinite words that has a run that visits some accepting state infinitely many times. Here, Q0 is the only initial state, and Q1 is the only accepting state. The language of A, when viewed as a Buki automata, is all infinite words that have only finitely many zeros. We denote by sigma the set of finite alphabet, and sigma star is all finite words above sigma. Sigma omega is all infinite words above sigma. We use three-letter acronyms to denote the classes of word automata. The first letter, D or N, indicates whether it's a deterministic or a non-deterministic automaton. The second letter, F or B, indicates whether it's an automaton over finite words or an automaton over infinite words with Buki acceptance condition. Languages in NFW, namely languages that are recognizable by a non-deterministic finite word automata, are also called regular languages. And languages in NPW, namely languages that are recognizable by a non-deterministic Buki word automata, are also called omega regular languages. Note that the automaton above is non-deterministic. At Q0, if we see a 1, we can either stay at Q0 or move to Q1. And the language of A is not recognizable by a deterministic Buki word automata. So DBW is a proper subset of NBW. A language R of finite words induces repetition languages of infinite words. Repetition provides a way of turning a finite behavior into an infinite one. We define 4 different repetition languages. The first is the limit language. The limit of R is all infinite words W, such that infinitely many prefixes of W are in the language R. Here in the drawing, we see that W has at least 5 prefixes in R. For example, if R is all finite words of odd length, then the limit of R is all infinite words. And if R is all sequences of zeros sandwiched in between ones, then the limit of R is the empty set. We state the following theorem proved by Landweber. An omega regular language L is in DBW, namely recognizable by a deterministic Buki word automata, if and only if there exists a language K, such that L is the limit language of K. The second repetition language is infinity R, or infinitely many R. Infinitely many R consists of all infinite words W, such that infinitely many disjoint subwords of W are in the language R. So words in infinity R looks as so. It has infinitely many disjoint subwords in R. For example, if we take R to be some sequence of zeros sandwiched in between ones, then infinity R is infinitely many ones. And if we take R to be the single word 0, 1, then infinitely many R is now infinitely many zeros and infinitely many 1. The third repetition language is R omega. R omega consists of all infinite concatenations of words from R. So words in R omega looks at so. And note that unlike infinitely many R, here we ask the infinitely many disjoint subwords to come exactly one after the other. So for example, if we take R to be all sequences of zeros that are sandwiched in between ones, then R omega is all infinite words that start with a 1 and then has infinitely many occurrences of 1, 1. And if R is a single word 0, 1, then R omega is a single word that alternates between 0 and 1. The last repetition language is R sharp. R sharp consists of all infinite words W, such that for all n greater than 1, there exists a prefix of W in Rn. So words in R sharp looks at so. It has a prefix in R, and also has a prefix that we can partition into 2 parts, each one in R. It also has a prefix that we can partition into 3 parts, each one in R, and so on. Note that R sharp can also be written as the following infinite intersection. Indeed, a word is in R sharp if and only if for every n greater than 1, it has a prefix in Rn. For example, if R is all sequences of zeros that are sandwiched in between ones, then R sharp is the same as R omega. And again, also for R that is the single word 0, 1, R sharp is the same as R omega, which is the single word that alternates between zeros and ones. To sum up, we define 4 different repetition languages. The limit of R is infinitely many prefixes in R. Infinitely many R is infinitely many subwords in R. R omega is infinite concatenation of words in R. And R sharp are words that have a prefix in Rn for all n. Some easy observations. R omega is always contained in R sharp. Indeed, if a word is in R omega, then we can partition it into an infinite concatenation of words in R. This partition also witnesses it's in R sharp. If R is regular, then the limit language of R, infinitely many R's, and R omega are all omega regular. This is not hard to show. In particular, it's not hard to construct an NBW that recognizes the language R omega. Given A, a DFW that recognizes the language R, we have that the Bookie language of A is the limit language of R. Here, LF of A denotes the language of A when viewed as a finite word automata, and LB of A denotes the language of A when viewed as a Bookie word automata. So the limit of R is in DBW for all regular languages R. It is also possible to construct a DBW for infinitely many R's. This is shown in the paper, and it's not a hard exercise. So is R omega in DBW for all regular languages R? This is the main question that started our study. We start with the easy case where R consists of only finitely many words. We have the following theorem. For every finite language R, we have that R omega equals R sharp equals the limit of R star. Recall that Landweber proved that omega regular languages are in DBW if and only if they can be expressed in terms of a limit operator. So we have the following corollary. For every finite language R, we have that R omega and R sharp are in DBW. In particular, we see here that R omega equals R sharp. So is R omega equal R sharp for all regular languages R? The answer is no, and the following is a counterexample. R consists of 2 types of words, either a single letter word $, or some word that starts with a 0 and ends with a 1, with some sequence of 0, $1 in between. Some observations about R. If X is in R and X contains a 1, then X is of the second type, which means that it starts with a 0. So if W is in R omega and W contains infinitely many 1s, then W contains infinitely many 0s. We prove that R omega is different than R sharp. Consider the following word. W starts with a 0 and follows by an infinite concatenation of words of increasing length. The ith word in the concatenation starts with a 1 and follows by I consecutive dollars. So here we see that W starts with a 0. The second word is the first word of the concatenation, which is a single letter word 1. The second word in the concatenation starts with a 1 and a single dollar. The third word in the concatenation starts with a 1 and $2 follow, and so on. W has infinitely many 1s, but only a single 0. Hence, W is not in R omega. Now, for any n greater than 0, consider the following prefix of W. Wn starts with a 0, and then we have only n parts of the infinite concatenation. Wn can also be written as follows. Subsequence of letters starts with a 0, ends with a 1, and then concatenated with n consecutive dollars. For example, W4 looks as follows. It has a first part that starts with a 0 and ends with a 1, then 4 consecutive dollars. W5 starts with a 0 and ends with a 1 at its first part, and then has 5 consecutive dollars. So W5 is in R6. and W4 is in R5. And in general, Wn is at Rn plus 1. So W is in R sharp, but not in R omega, which shows that R sharp and R omega are different. So R omega equals R sharp needs not hold for all regular languages R. We know that R omega is an NBW. It's easy to construct an NBW for R omega. But it's not clear that R omega is the limit of some language. Recall that this is a necessary condition for it to be in DBW. We have the following theorem. For all regular languages R, the following are equivalent. R omega equals R sharp, R omega is in DBW, and R sharp is omega regular. We sketch the proof of two directions, and the last direction can be found in the paper. We prove that if R omega equals R sharp, then R omega is in DBW, and R sharp is omega regular. Note that the second part is easy. If R omega equals R sharp, then since R omega is omega regular, so is R sharp. For the first part, we use Landweber's topological characterization of DBW languages. Landweber proved that an omega regular language L is in DBW if and only if there exists a sequence, Ki, of languages of finite words, such that L can be written at the infinite intersection. Namely, a word is an L if and only if, for every I greater than 1, there exists a prefix of the word and Ki. Note that the language R sharp satisfies Landweber's topological condition. In fact, this is why we defined R sharp to begin with. We have the following corollary. For every regular language R, if R omega equals R sharp, then R omega is in DBW and R sharp is omega regular. Indeed, if R omega equals R sharp, then R omega satisfies Landweber's topological condition. So it is in DBW. The second direction is to show that if R sharp is omega regular, then R omega equals R sharp. We use the definition of lasso-shaped words. Lasso-shaped words are infinite words that start by some finite word U and then loop some finite word V. We have the following lemma. R omega and R sharp agree on all lasso-shaped words. We sketch the proof of lemma 1. We need to show that all lasso-shaped words in R sharp are also in R omega. We consider our word W, which is a concatenation of U with V to the omega, so it's of lasso shape, and we assume it to be in R sharp. Let N and K be the length of U and V, respectively. Let Y0 be in Rn, and Y1 up to Yk be in R, such that the concatenation of Y0 up to Yk is a prefix of W. W can be drawn in two ways. The first is using its lasso shape. It starts with a U and follows by an infinite concatenation of V's. The other is using the prefix we constructed. Note that Y0 is in Rn, and N is the length of U. This means that the U is shorter than Y0. It follows that all last letters of the Yi are positioned in the V segments of W. We took K plus 1 different Ys, and the length of V is K. So there exist two different Ys, Yi and Yj, that end at the same position inside V. We see this in the following drawing. Here Y0 up to Yi ends at the same position that Yi plus 1 up to Yj end in V. And note that Y0 up to Yi is in R star and Yi plus 1 up to Yj is in R star. Now W can be written also in the following form. It is the concatenation of Y0 up to Yi with the omega of the concatenation of Yi plus 1 up to Yj. So W is in R omega, which is what we wanted to show. So we proved our first lemma. R omega and R sharp agree on all lasso-shaped words. The second lemma is that two omega regular languages, L1 and L2, are equal if and only if they agree on all lasso-shaped words. We sketch the proof of lemma 2. Let A be an NBW that recognizes a different language of L1 and L2. We have that L1 is different than L2 if and only if the language of A is not empty. And this happens if and only if there exists a lasso-shaped word in the language of A. namely some word that is obtained by a finite path from an initial state to an accepting state, and then by a cycle from the accepting state to itself. So we have the following corollary. By lemmas 1 and 2, if R sharp is omega regular, then R omega equals R sharp. We saw that R omega equal R sharp does not hold for all regular languages R, and that R omega equals R sharp is equivalent for R omega being in DBW. In particular, the language we saw before is such that its omega language is not in DBW. Now it's natural considering the decision problem of is R omega in DBW? We have the following theorem. Given an NFW A, deciding if the omega language of A is in DBW is p-space complete. The upper bound is straightforward. Given an NFW A with n states, it's easy to construct an NBW A prime with n plus 1 states that recognizes the omega language. Then deciding whether the language of a given NBW is DBW recognizable can be done in p-space. For the lower bound, we give a log space reduction from the universality problem of NFWs. This is proved to be p-space hard. We saw that R sharp needs not be omega regular. The sharp operator replaces the infinitely many nature of the omega operator with an unboundedly many one. We examine an analogous change in the definition of acceptance in Buki automata. Let A be a non-deterministic automaton with an accepting set of states alpha. The sharp language of A is all infinite words W, such that for every n greater than 1, there exists a run of A on W that visits alpha at least n times. Note that unlike Buki automata, where we ask for a single run to visit alpha infinitely many times, here we ask for possibly infinitely many different runs that visit alpha unboundedly many times. Also note that for deterministic A, we have that the Buki language of A and the sharp language of A are equal. This is because there is only a single run. Consider first the following example. Here A has a single initial state Q0, which is also the single accepting state. When viewed as a finite word automata, A consists of the word dollar. It also consists any sequence of dollars. It consists also words that start with a 0, then has some sequence of letters and ends with a 1. And in fact, the language of A when viewed as a finite word automata is R star when R is the language we defined earlier. Consider the following word. Recall that W is the word we use to show that R omega is different than R sharp. We consider now a possible run of A on the word W. So we start from Q0, and then we see the letter 0. We have to move to Q1. From here, we can stay at Q1 as long as we want. Let's consider the case where we stayed at Q1 until we see someone that precedes $4. For example, this one. So we see that one, and we move to Q0. Then we see $4 signs. So we cycle at Q0 4 times. This means that overall by now we saw Q0 5 times. Now we're going to see another letter 1. So we move to Q2. And Q2 is a rejecting sync, so we're going to stay here forever. Note that like we constructed this one that visits Q0 5 times, we can construct a run that visits Q0 n times for every n greater than 1. This means that W is in the sharp language of A. Now it's also possible to show that W is not in the Buki language of A. All infinite runs of A on W eventually get stuck at Q1 or at Q2. So W is in the sharp language of A, but not in the Buki language of A. In fact, one can show that the sharp language of A is R sharp, and the Buki language of A is R omega. The relation between the sharp language of A and the Buki language of A is similar to the one obtained for R sharp and R omega. For all finite automata A, the following are equivalent. The sharp language of A is omega regular. The Buki language of A equals the sharp language of A, and the sharp language of A is in DBW. We summarize the translation from an automaton for R to an automata for its repetition languages. All translation exists, but for the one from a DFW to a DBW for the omega language. We saw that there exists a regular language R, such that R omega is not in DBW. We consider now also the succinctness, namely the blowup in translation. Given a DFW or an NFW with n states, how many states are needed for a DBW or an NBW for the repetition language? We address two of these blobs which are significant. The first is from a DFW to a DBW for infinitely many R. Here there is an exponential blob. The following diagram shows why. We start with a DFW for R. Then there is no blowup when going to an NFW for sigma star concatenated with R. Then, by using determinization, there is an exponential blowup going to a DFW for the same language. And in the last step, there is no blowup when going to a DBW for infinitely many R. So this step is essential, and we show this in the paper. The second blowup is from going from a DFW to a DBW for R omega. There is a 2 to the O of n log n blowup. Here we start with a DFW for R. There is no blowup when going to an NBW for R omega. And finally, by determinizing, we have a 2 to the O of n log n blowup when going to a DBW for R omega. That's all. Thank you all for listening.